You thought we were moving on to vapor pressure, didn't you? Instead, I want to look at this graph again. So we kind of qualitatively looked at what's happening at each section of the graph, what the particles are doing. Are they moving faster, or are we adding energy to change phase and overcome intermolecular forces? What I want to do now is calculate exactly how much energy is required to change phase or to increase the temperature. So we're going to pull out our calculators, and let's say this is, I don't know, let's just pretend that it's a 100-gram sample. So we'll make note of that. Let's pretend we have 100 grams of ice. We're starting with 100 grams of ice. And I want to know how much energy has to be added to increase the temperature from -20 to 0 degrees Celsius. Okay, so we already kind of mentioned this bottom section of the graph here. That's the solid phase. Obviously, the temperature is increasing. So we can use that equation, delta H equals, I'll do it the AP way. On the AP packet, it's actually listed as Q, heat capacity. Q equals MC delta T. Let's do it that way. M stands for mass, so in the problem that would be given to you, I just randomly picked 100 grams because it seems like an easy number to use. So I got 100 grams. I'm going to multiply that by C, the specific heat, which is something that you'd be given in an AP problem. In the homework, you'll look it up on a chart. Now, water's kind of funky because it has a different specific heat value depending on the phase. Most substances just have one specific heat regardless of phase. So if you're doing a problem with water, just be a little bit careful that you use the right phase. So I would know that anywhere between 0 and -20, this is water in the solid phase. And so I would look this number up on a chart. It's excellent. I need some college credits. 2.03 joules per gram degree Celsius would be the unit. And again, that would mean that it takes about 2 joules of energy to raise 1 gram of ice up 1 degree. Well, I have 100 grams, so I multiply that by the mass. And we're going to go 20 degrees, so we multiply it by the temperature change. And we should maybe make note of that. Temperature change is temperature final minus temperature initial. Not that you have to show work for it, but that's where we get the 20-degree temperature change. Or you get it off the graph, duh. So we plug this in our calculator, and I'm not going to pick on sig figs too much here. I just want to get kind of an example of how to use these equations. So let's plug this in and say it's like 4,060, and your unit is joules. The specific heat was measured in joules per gram degree Celsius, so my final answer is in joules. You can use this equation whenever there's a temperature change. So again, be careful if you're doing these calculations in the homework. Sometimes that's the hardest part. They don't know what equation to use. If the temperature is changing, this is your equation, and it's great because this is an easy one. So anywhere in this section of the graph, the temperature is changing. Q equals mass, which would still be 100 grams, times temperature change, 100-degree temperature change. I should put this in the order of the other one. Specific heat. Specific heat, if you look it up for water in the liquid phase, 4.18 joules per gram degree Celsius. And then we'll do the temperature change at the end. 100 degrees. So in the book, it'll say mass times temperature change times specific heat, but I'll put it in the order of the AP packet. Because again, you don't want to memorize these equations, just look them up. Just know where to find them in the packet, what's available, and how to use them. So if we plug this in our calculator, and we just kind of use some nice numbers, 41,800 joules. Yikes. And if I wanted to, then I could do this up at the steam section as well. So I'll just make a note of that. If I was doing anything up in here, if I had water and maybe they said, you're going to increase the temperature from 120 to 140 degrees, well then I could use this same equation. Q equals mass times specific heat times temperature change. For water, you just have to make sure that you use the specific heat in the gas phase, and you'd look it up. Now you cannot use this equation at the other sections of the graph because we mentioned there is no temperature change. And obviously heat is still being added. So we use the other equation at this first section of the graph. The melting point, we're going to say Q, or heat, delta H, equals moles times heat of fusion. And again, heat of fusion is a constant. You look it up on a chart or on the AP test. All of these constants would just be given to you right in the problem. First thing I need to do then is get some moles. I have 100 grams of water. So we'll do a little sidebar. Cancel grams, we need moles. 1 mole should be about 18.02 grams. How nerdy, but after a while you kind of start memorizing the molar mass of water. So let's use this as, let's say 5.55. Let's pretend this was like 100 grams exact. And I just made up the 100 grams. There was no mass given. Okay, so now we can plug this in. Moles. 5.55. And then again, heat of fusion is a constant. You would look it up on a chart, which I will do right now. Heat of fusion for water, 6.00 kilojoules per mole. So again, here's kind of why they don't give you this equation in the AP packet, because they think that you're relatively smart, and you could figure it out that if you have 6 kilojoules to melt 1 mole, and you have 5.55 moles, you would know to multiply. I think we could figure that out. Okay, so let's go like 3 figures and say this is 33.3, and I have to be a little careful. Kilojoules. This is annoying, but something to be on the lookout for. Specific heat values are always reported as joules per gram degree Celsius, are usually reported in joules. But heat of fusion is usually reported in kilojoules per mole. So just be a little careful if you are doing multiple calculations. Those units might be different. We'll deal with that in a minute. And now let's say I want to do the same thing up here through this boiling point. At the boiling point, Q, or energy, delta H, would be moles times heat of VAP. Vaporization, which is another constant. You look it up on a chart, which I will do, and I will say that this is about 40.6. Okay, so we got our moles, which is still 5.55, and then it's 40.6 kilojoules per mole. The amount of energy required to boil or vaporize 1 mole of water. And so we plug this in our calculator, and we'll leave something that's relatively reasonable. So with maybe 3 sig figs or so, we'll say it's like 225 kilojoules. Okay, so there's an example of how to use these 3 equations. These aren't hard equations to use. The most common concern I usually hear is that people don't know when to use which equation. If the temperature is changing, you use your mass times specific heat times temperature change. If you are changing phase, you'll use moles times heat of fusion or moles times heat of vaporization. here's where you have to be careful. What if the question says, calculate the energy required to change 100 grams of ice at negative 20 degrees to water at positive 20 degrees? Do you know the most common mistake people will make? They'll say, oh, cool, temperature change. We're going negative 20 to positive 20. That's a 40-degree temperature change. Excellent. So then they go mass times specific heat times 40-degree temperature change. We're done. Uh-oh. Be very careful, especially with water, because they're going to expect that you know water melts at 0 and boils at 100. If the range of temperatures includes a phase change, you have to add in that energy. And this always catches people, that if I go from negative 20 to positive 20, not only am I increasing the temperature, but I'm also melting the substance. I'm going through a phase change. So you have to add in the amount of energy required to change the phase. Then you'd add them all up. So for example, if the question said, like, I'm going from negative 20 degrees to 100, then I would have to add these together. I would have to take, okay, I'm going to add about 4,000 joules to increasing the temperature up to 0. Then I have to add about 33 kilojoules to melt the substance. Then once it's all liquid, I'm going to add almost another 42,000 joules to increasing the temperature. In the end, then, I would add them up. And again, here's where you have to be a little careful, because that heat of fusion was in kilojoules. So before you add them, just make sure that they're all the same. I don't care if it's joules or kilojoules, as long as you change them so that they're all the same before you add them. So again, these aren't difficult equations to use, but they definitely require a little bit of practice so that you kind of catch some of these little tricks, like that going through a phase change thing that I'm sure you'll see in the near future. And I'm sure you'll all get it right now.